Hello and welcome to the section 11.4 lecture today. 11.4 is kind of split up into 2 days, but I've just labeled them 11.4 and 11.5. And today we're going to mainly focus on calculations, and on the next day we're going to look a little bit more at graphs. So let's go ahead and jump right into it. I'm going to go ahead and give myself a calculator today, because I feel like I'm going to need it. Okay, not too bad. Let's actually, does it work if I do that? No. Let me zoom this in just a little bit. We don't really need the space off to the side. So 200 is nice, but I think 300 will be better. Better? No, we're going to go back to 200. Okay then, be that way. Anyways, so we've worked with exponents in the past, but typically we've been dealing with a variable being raised to some power. Okay, and I say some constant power because constant being the opposite of variable. But today we're going to look at what happens when the variable is actually in the exponent position, not in the number being raised to the exponent position. We call it the base. Like in this first problem, 3 is the base and x is the exponent. So I want to look at different values of x and see what their corresponding y values would be. This is kind of like a t-chart that I'm making here, but just horizontally instead. So that I can kind of think about what this means. This first one means 3 to the 0 power. And I don't need a calculator for that. We have a rule for that. That equals 1. What about 3 to the first power? Well, that's just 3. 3 to the second power is 9. 3 to the third power, 9 times 3, 27. And we should see that every single time, all I'm really doing is multiplying by 3. And so that can be a quicker way of filling out the rest of it, because on a calculator, it's tough to know which way. There's this X to the Y button here. And some calculators, to get this one, you would have to go 4 and then 3, 4 button and 3. On this one, you would actually, okay, that's going to do weird stuff. No. This one, you do hit 3 to the 4th power. But I have come across calculators in the past that you have to do that in the reverse order, and I can never figure out why. But you do. But it's probably easier just to take 81, multiply it by 3, 243, and take that and multiply it by 3, 720. Hello. 729. Okay. Let's see if the same thing holds true with a negative 2. For negative 2, if I raise that to the 0 power, I still get 1. Negative 2 to the first power, I get negative 2. Negative 2 to the second power, I get positive 4. What about negative 2 to the third power? Negative 8. And all this is still working out that I'm multiplying by negative 2, and then negative 2 times negative 2, and then 4 times negative 2. But something interesting is happening with my values here, that they're alternating between positive and negative. Numbers-wise, they're kind of what we expected. 1 times 2 is 2, 2 times 2 is 4, 8, we'd have 16 here. This one flips back to a negative and it's 32, and then finally a positive and it's 64. So with negative numbers there, we get some weird things that happen. Kind of bounces around a little bit. Let's look at an example of where this might be used. So advancing technology. Let's say that the new cell phone just hit the market, and in town, 10 people bought it on the first day. On the next day, they each convinced one of their friends to buy the same phone. So let's say that day 0 is that first day. Okay. And on that day, there's 10 people that own it. After a day, each one of them told one of their friends to buy the phone. Well, how many would I then have? If each one of them convinced one of their friends, there were the 10 original people that owned it, each one of them plus one friend, so now there's 20. If after this day, those new 20 people, or those 20 people each convinced another one of their friends, so for the original 10, now they've convinced another friend, but here we have the 20 people, and they each convince one friend, and we get 40. On 3, we get 80. After 4 days, it's 160, then 320, and then how many people after 10 days? Well, let's look at it this way. Every day it doubles. So 20, 40, 80, 160, 320. That's after 5 days. 6 days, 7 days, 8 days, 9 days, 10 days. So after 10 days, if this were able to continue, odds are it wouldn't, but just in case, 10,240 people would own the phone on that day. Now, I'm going to go ahead and leave 50 up to the belief of whoever wants to do it, or I'll figure it out later, one or the other. You could just keep hitting equals on the calculator, but then you got to track all the way to 50 days. Okay, and my graph's not going to go that far anyways, so I'm not that worried about it. After day 1, 10 people on the phone, on day 0, 10 people on it. Day 1, 20 people on it. On day 3, day 2, we have 40 people, and then 80 people, and then 160 people. Trying to find out where that is. That's right there. And then on day 5, 320 people. So we see this growth, and again, we're not dealing with a straight line here. We have a curve. Try to make it as smooth of a curve as I can. Okay, we have a curve that looks like that. Now, obviously, not everything is going to grow this way. You have things like population that's eventually going to slow this back down. At some point, you're going to have more people that own the phone than that don't own the phone. And some of them just may not want it. So then it's going to start leveling out. And then obviously, if this were to continue indefinitely, eventually you'd hit your max number of people and it wouldn't work out anyways. Okay? But this brings us to a general form of an exponential function. These are exponential functions where I have y equals a times b to the x power, where a, how do I want to say this? I'm going to call this the starting value. And B, kind of the growth rate. Now, there are specific requirements for A and B. But if I think about this and about this equation in this setup, I really had y equals, or the number of people that own the phone after X number of days was, the starting value was 10, and the growth rate was that it doubled. So that's going to be a 2 to the X power. Okay, and just to double check that that works out, when X is 0 on day 0, 2 times 0, 2 to the 0 power is 1. 10 times 1 is 10. If 2 is being raised to the first power, 2 to the first power is 2. 10 times 2 is 20. So using this, we can actually figure out what it would be after the 50th day. Okay, but I would need 2 to the 50th, not 500th. 2 to the 50th. That's a big number. Now I want to take that and multiply it by 10. Guess what? Even bigger number. Million, billion, trillion, quadrillion. So there would only be 11 quadrillion people in town that would own the phone. 999 billion, 68 million, 426,240 people that would own this phone. It's taken over everything. Obviously, there are things that get in the way. Population is a big one. There aren't that many people, so we don't have to worry too much about this same pace lasting for 50 days. Let's go ahead and take a look at what happens if b is a fraction. What if I have a 1/3 that I'm raising to the xth power? Let me start it at 0. Okay, 1/3 to the 0 power is going to be 1. 1/3 to the first power is going to be 1/3. And so it looks, to get from here to here, I could look at it two ways. I'm probably going to look at it the multiplication way, but I'm multiplying it by 1/3. Kind of like dividing it by 3. So as I move this way, I multiply by 1/3, just as I did before. And now as I move backwards, I end up dividing by 1/3. Dividing the answer that I had by 1/3. Just to finish out this way, 1/3 times 1/3 is 1/9. So it's getting smaller this way. Going backwards, if I take 1 and I divide it by 1/3, remember we don't really divide fractions. I would keep change flip and multiply by 3/1, which is to say multiply by 3. So as I go this way, I end up multiplying by 3. In a similar way with 1/4, at 0 it's 1, at 1 it's 1/4. 1/4 times 1/4 is 1/16, but going backwards I would multiply by 4 and multiply by 4. So if we were to think about graphs of these ones, which we're not going to, whereas the phone example escalated as time went by, these ones, when they're negative, they're big numbers, 16 and 9, and then they come down to 0, and they flatten out towards 0. Sorry, they come down to 1, and they flatten out towards 0. Okay? Whereas the phone one, if I would have picked negative numbers to put in there, would have started out really close to 0, gone through 0, 1, and escalated pretty quickly. And these are the two opposites here. This is when b is greater than 1, and this is when, I'm going to write it this way, when b is between 0 and 1, when b is a fraction. Okay, and then the a number is just that starting value, right? If I had in this one x equal to 0, 1/2 to the 0 is 1, negative 2 times 1 is negative 2. If x was 1, 1/2 to the first power is 1/2. Negative 2 times 1/2 is negative 1. If I raise it to the second power, 1/2 or 0.5 to the second power, I get 0.25 or 1/4. And 1/4 times negative 2 would be negative 1/2. Negative 2/4. So in this pattern, I am really starting at negative 2, and I'm dividing by, well, let's call it what it is, multiplying by 1/2 going this way. On this way, I would divide by 1/2, which is like multiplying by 2. And so I get this pattern. Okay, now let's talk about another application of this that comes to what we call half-life. Half-life is really deals in the bacteria world and kind of the science world. But bacteria decays over time. And specifically with half-life, this is going to tell us how much time for half of whatever to, I'm just going to say perish. It might die, it might dissolve, it might do whatever, okay? But that shows us how much time it takes for something to, you could even have a half-life of a population. And you could say that over 10 years, half of that population is going to go away. Whether they move out, whether they pass away, whatever it might be. So and this is a half-life formula. This shows us how to find the half-life. And so the n with the t in parentheses is going to be the amount left after t time. The n with a 0 down below is the initial amount, the starting amount. The t is the amount of time that has passed. And the t with the little 1/2 is what we call the half-life period. And it is that thing that I talked about before, the amount of time that has to go by for half of it to be left. Okay, so in this first one here, it says the half-life of iodine 125 is 60 days. What fraction of iodine 125 would be left after 360 days? So we don't have an initial amount on this problem, so we're just going to consider it to be 1. And then our answer is going to tell us how much is left. Okay, so our n0 is going to be 1. Our t, the time that we want to make pass by, is 360 days. And the t to the 1/2, the half-life, is 60 days. Okay, so we want to find n of t for a t0 of 1. So I'm just going to say that I'm not going to have that 1 there. I'm just going to go 1/2 times the time I want to go by, 360, divided by 60. And now this part is kind of interesting because it tells us how many iterations of a half-life are going to occur in the amount of time that we want to look at. Because 360 divided by 60, we might know that as 6. So we're trying to see how much is left after 6 half-lives. Okay, so we really have n of t is equal to 1/2 to the 6th power. Well, we do want to know it as a fraction, but maybe I can turn it into a fraction. Maybe not. Maybe not. So I guess our best bet there is to raise 2 to the 6th power and then put it under 1. So that's 64. So this would be 1/64. So there's 1/64 of the iodine 125 of the original amount left after 360 days. And the other thing that's kind of interesting with this is if you keep working this out and pick bigger and bigger spans of time, technically the iodine 125 or whatever thing we're talking about here is never going to fully go away. There might be, you might get, 1/64 isn't very much, but still there's never going to be none of it left, which is an interesting thought. It's like this. If I go ahead and look at the wall that's farthest away from you, wherever you're at, and think about walking halfway. Now that you have a new spot determined, walk halfway again. Walk halfway again. And keep walking halfway from the new spot that you have halfway to the wall. You're never going to technically reach the wall. Now, of course, physical nature tells us that, we probably are, but technically you're never going to reach that wall. And it's the same thing with half-life. We're never going to fully get rid of it if all that ever happens every one of these iterations is that half of it goes away. We're never going to fully get rid of it. Let's look at this one. Fluorine 21 has a half-life of 5 seconds. How much of the starting 50 grams? So on this one, I have a starting amount of 50. And it told me that the half-life was 5 seconds. I'm just trying to write in what I have as I get it. But how many, or how much of the starting 50 grams would be left after 1 minute? Well, the only issue here is that I want a time that's also in seconds, and 1 minute is 60 seconds. So setting this up, we have 50 grams that we're starting with. The 1/2 always goes in there. The time that I want to pass is 60 seconds, and the half-life time is 5 seconds. So we want to look at 12 half-life cycles. So we have 50 times 1/2 to the 12th power, and I'm just going to plug it in and deal with the decimal that I get. I'm actually going to do the 1/2 to the 12th first. It's going to be a very small decimal, and I'm going to multiply that by 50. So you might think, well, there's not much left. Kinda. What this comes to do, or what this comes to be, is 50 divided by 2, divided by 2, divided by 2, divided by 2, 5, 6, 7, 8, 9, 10, 11, 12. And I believe that's what I had. I might be off by 1, but I might have hit it too many times. Let's go ahead and check again. 50 times, do the 1/2 first. 1/2 to the 12th times 50. Nope, I think I hit it just right. So what's left? 0.0122 grams. Not much of it, in other words. And that is a 0. I know that's hard to see. But anyways, if you have any questions, make sure you get them written over on the side. Otherwise, I hope you have a great day, and we will see you in class.